Right now, as you settle in and let the weight of the day begin to fade, I want you to consider something, not as a thought experiment, not as a metaphor, but as a possibility rooted in mathematics, physics, and the actual structure of the universe you are floating through at this very moment. You may have lived this exact life before, not a similar life, not a life that rhymes with this one or loosely resembles it, this exact life. Every breath, every stumble, every quiet evening just like this one, where you lay still and listen to someone talk about the stars, the laugh you let out last Tuesday, the way the light caught the window this morning, the very decision to press play on this video. All of it, down to the last atom, may have already happened. Not once, not twice, but trillions upon trillions of times, stretching backward through a corridor of time so deep that the word forever barely scratches the surface. This is not reincarnation. This is not mysticism or metaphor. This is what happens when you follow the laws of physics all the way to their conclusion. When you take what we know about the size of the universe, the number of particles it contains, the nature of time, and the behavior of black holes, and you simply refuse to look away from what the math is telling you, the answer it gives back is unsettling and beautiful, and so enormous that most people never sit with it long enough to feel its full weight. Tonight, we are going to sit with it. Before we drift further into the loops of time, please take a moment to like this video and subscribe to Cosmic Drift. It helps us continue exploring these deep cosmic mysteries together. Now, to understand how physics arrives at the staggering conclusion that your life may be an eternal loop, we need to start with a question that sounds simple, but contains the entire mystery within it. How much information can the universe hold? Not how much information does it hold right now, but how much could it possibly hold if every atom and every particle were arranged in every conceivable way? Because if that number is finite, if there is a ceiling, a cap, a hard limit on how many different ways the universe can arrange itself, then something extraordinary follows. Given enough time, every possible arrangement must occur, and then it must occur again, and again, and again. Not because the universe is trying to repeat itself, but because it simply runs out of new things to try. This idea might sound like philosophy, and in a sense it is. But the ceiling is real. It was discovered by a physicist named Jacob Bekenstein in 1981, and it has been confirmed and refined by decades of research since. It is called the Bekenstein bound, and it sets a hard physical limit on the amount of information that can exist in any given region of space. Not a soft limit, not an estimate, a wall, a boundary written into the fabric of reality itself, as firm and unyielding as the speed of light. To understand the Bekenstein bound, think of it this way. Imagine you have a room, a simple room, maybe the size of your bedroom. Inside that room, there is a certain amount of energy. The walls define a certain volume of space. Bekenstein showed that the maximum amount of information that can be stored in that room is not infinite. It depends on only two things: the size of the room and the amount of energy inside it. That is it. No matter how clever you are, no matter how many tiny particles you cram into that space, there is a maximum number of distinct arrangements those particles can take. Once you reach that number, there are no more options. Every possible configuration has been exhausted. The formula itself is elegant. The maximum entropy, which is the physicist's word for the number of possible arrangements, is proportional to the radius of the region multiplied by the energy it contains. Divide by a few fundamental constants of nature and you get a number. A large number to be sure, staggeringly large, but finite, always finite. This was proven rigorously in 2008 by the physicist Horacio Cassini, using a tool from quantum information theory called quantum relative entropy. The proof showed that Bekenstein's original intuition was not just a good guess. It was a law. The universe does not allow infinite information in a finite space. Period. Now, why does this matter for the question of whether you have lived before? Think of it like a deck of cards. A standard deck has 52 cards. If you shuffle that deck, there are an enormous number of possible orders the cards can appear in. The number is roughly 8 times 10 to the 67th power. That is an 8 followed by 67 zeros. It is a number so large that if you shuffled once per second since the Big Bang, you would not have come close to trying every arrangement. And yet, that number is finite. It is not infinite, which means if you kept shuffling forever, eventually you would get the same order twice. You would have to, because you have run out of new arrangements. The universe works the same way, only the deck is much, much larger. Instead of 52 cards, you have every particle in the observable universe, every quark, every electron, every photon. The Bekenstein bound tells us that even this enormous deck has a finite number of arrangements. The number is so large that writing it down would fill more pages than every book ever printed. But it is finite. It has an end. And that means, given enough time, every possible arrangement of matter and energy will occur, including the exact arrangement that makes up you right now, in this moment, listening to these words. This is the foundation upon which everything else we discuss tonight is built. The universe has a finite number of possible states. Time, as far as we can tell, does not. And when you combine a finite number of states with an infinite amount of time, repetition is not a possibility. It is a certainty. But we are getting ahead of ourselves. Because the question of whether time truly is infinite, whether the universe stretches forward without end, is itself one of the great unsolved puzzles of modern physics. And to understand the most extraordinary answer to that puzzle, we need to talk about a man who has spent more than half a century staring at the deepest structures of reality and finding things there that nobody else could see. A man who, at the age of 89, won the Nobel Prize in Physics. A man who collaborated with Stephen Hawking, who invented new forms of mathematics to describe the geometry of the cosmos, and who, in the summer of 2005, while thinking about the far future of the universe, had an idea so bold that he himself called it outrageous. His name is Roger Penrose, and his idea is called Conformal cyclic cosmology. To understand what Penrose proposed, you first need to understand the problem he was trying to solve. And the problem begins with one of the most basic observations in all of science. Things fall apart. Ice melts, buildings crumble, stars burn out. This is the second law of thermodynamics, and it is one of the most ironclad rules in all of physics. Entropy, which is the measure of disorder in a system, always increases. The universe moves inexorably from order to chaos, from structure to smoothness, from hot, dense clumps of matter to a thin, cold, uniform nothing. If you follow this law forward in time, the picture it paints of the far future is bleak. Trillions of years from now, long after our sun has died and our galaxy has gone dark, the universe will continue to expand. The distances between galaxies will grow so vast that light from one will never reach another. Stars will burn through their fuel and flicker out. The last red dwarfs, those small, stubborn stars that burn their hydrogen slowly, will finally exhaust their reserves and go cold. The universe will become a graveyard of dead stars, cooling cinders, and wandering particles drifting through an ever-expanding void. But even that is not the end, because scattered across this dark cosmos will be objects of extraordinary power and patience. Black holes. These remnants of collapsed stars and merged galaxies will be the last major structures in the universe, and they will endure for timescales that make the current age of the cosmos look like the blink of an eye. A black hole with the mass of our Sun would take roughly 10 to the 67th power years to evaporate. That is a 1 followed by 67 zeros. And the supermassive black holes at the centers of galaxies, the ones that contain billions of solar masses, would last even longer. Perhaps 10 to the 100th power years, a googol of years. But even they are not eternal. Because in 1974, Stephen Hawking made one of the most remarkable discoveries in the history of physics. He showed that black holes are not truly black. They emit radiation. Slowly, imperceptibly, over timescales that dwarf anything in human experience, black holes lose mass. Particle by particle, photon by photon, they evaporate. Hawking radiation, as it came to be called, is not what most people think it is. The popular image is of particle and antiparticle pairs popping into existence near the event horizon, with one falling in and the other escaping. Hawking himself used this picture to explain the concept in simple terms. But the actual mechanism is more subtle. It arises from the curvature of space-time itself near the black hole. The intense warping of space and time generates a constant, faint glow of thermal radiation. The energy for this radiation comes from the black hole itself, causing its event horizon to slowly shrink. Over eons, this process accelerates. The smaller the black hole gets, the hotter it burns, until in its final moments it erupts in a burst of light and energy and is gone. In 2023, researchers at Radboud University made a remarkable finding that expanded this picture even further. They showed that Hawking radiation is not unique to black holes. It occurs wherever space-time is curved. This means that, in principle, every massive object in the universe, not just black holes, emits a form of this radiation. Everything, given enough time, slowly dissolves back into the fabric of space. The universe, it seems, is a patient eraser. So what happens after the last black hole evaporates? What remains when every structure has been dismantled, every particle has decayed, and the universe is nothing but a thin bath of photons and gravitons stretching across an incomprehensibly vast emptiness? This is the state that physicists call heat death. Maximum entropy. A universe with no gradients, no structure, no difference between one place and another. A cosmic flatline. For most physicists, this is where the story ends. The universe was born in the Big Bang. It expanded. It formed stars and galaxies and planets and people. And then, over inconceivable stretches of time, it all faded away. A single arc from order to chaos, from something to nothing. But Roger Penrose looked at this picture and saw something that nobody else had noticed. He saw a strange symmetry. The very far future of the universe, that thin soup of massless particles drifting through infinite space, looked remarkably like the very beginning. At the Big Bang, the universe was also unimaginably smooth. It was also dominated by radiation rather than matter. And the particles at the very beginning, just like the particles at the very end, were moving at or near the speed of light. This is where Penrose's idea took shape. He realized that particles moving at the speed of light have a peculiar property. They do not experience time. For a photon, for a particle of light, the journey from one side of the universe to the other happens in an instant. From the photon's perspective, there is no passage of time at all. And if there is no time, there is no way to measure distance. A universe 1 inch across and a universe 1 trillion light-years across are, to a photon, the same thing. They are indistinguishable, because without clocks, there is no scale. This is the key, the deep mathematical insight at the heart of conformal cyclic cosmology. When the universe has expanded to the point where only massless particles remain, it loses the ability to keep track of how big it is. Size becomes meaningless, and if size becomes meaningless, then the vast, cold, empty future of one universe is mathematically identical to the tiny, hot, dense beginning of the next. The end becomes the beginning, not through a collapse, not through a bounce, but through a transformation. A conformal rescaling in the language of mathematics. The shape of space-time is preserved. The angles, the relationships between points, the geometry of light, all of it carries over. Only the scale changes. And since scale no longer matters, the change is invisible, seamless. The universe simply continues. Penrose calls each cycle an aeon, and in his model, the universe is not a single story with a beginning and an end. It is an infinite sequence of aeons, each one born from the ashes of the last. The Big Bang that started our universe was not the beginning of everything. It was a transition, a doorway between what came before and what comes next. This is conformal cyclic cosmology, CCC, and when Penrose first presented it between 2005 and 2010, and formalized it in his book Cycles of Time, it sent a ripple through the physics community, not because everyone agreed with it, far from it, but because it was elegant, it was mathematically precise, and it came from one of the most respected minds in the history of mathematical physics. To appreciate the weight of this idea, you need to know who Roger Penrose is. Born in 1931, Penrose has spent more than 7 decades working at the deepest levels of physics and mathematics. In the 1960s, he proved that the formation of black holes is an inevitable consequence of Einstein's general relativity. This was not an obvious result. Many physicists at the time believed black holes were mathematical curiosities, artifacts of equations that would never appear in the real universe. Penrose showed they were not optional. They were guaranteed. Any sufficiently massive object that collapses under its own gravity must form a singularity, a point of infinite density, where the known laws of physics break down. For this work, he shared the 1988 Wolf Prize with Stephen Hawking and was awarded the Nobel Prize in Physics in 2020 at the age of 89. But Penrose's contributions extend far beyond black holes. He developed the mathematical tools known as Penrose diagrams, which allow physicists to map the entire history of the universe onto a single page. He discovered a form of non-periodic tiling now called Penrose tiling, which has deep connections to the structure of certain crystals and to the mathematics of symmetry itself. He has written on the nature of consciousness, on the foundations of quantum mechanics, and on the relationship between mathematics and physical reality. He is, by any measure, one of the great scientific minds of the modern era, and he is still working. As recently as March 2025, Penrose, now in his 90s, published a new paper with his collaborator, Christoph Meissner. The paper introduced what they call the gravitational wave epoch, a phase in the transition between aeons that they argue makes the crossover smoother and more physically plausible. They also proposed a mass and energy conservation law that operates across the boundary between aeons, The work shows that CCC is not a static idea. It is still evolving, still being refined, still being pushed forward by the mind that created it. So what would it look like, this transition between aeons? Let us walk through it, not in the abstract, but step by step, from the world we know to the world that might come next. Start here. Start now. The universe is 14 billion years old. Stars are burning. Galaxies are spinning. Planets are orbiting. You are lying, here, breathing, existing. This is our aeon. It began with a Big Bang roughly 13.8 billion years ago, and it will continue for a very, very long time. Fast forward. A few trillion years from now, the last stars go dark. The universe is a sea of dead remnants. White dwarfs, neutron stars, black holes. The temperature of the cosmic background radiation has dropped to nearly absolute zero. Space continues to expand, driven by dark energy, pushing everything further apart. Keep going. Over timescales of 10 to the 40th power years and beyond, the remaining matter begins to decay. Protons, the building blocks of atoms, may not be eternal. Several theoretical frameworks predict that protons eventually fall apart into lighter particles. This has never been observed, and experiments have pushed the lower limit on the proton's lifetime to, at least, 10 to the 34th power years. But many physicists believe it will happen eventually. If it does, then all ordinary matter, every atom in every dead star and wandering rock, will eventually dissolve. Further still, the black holes remain, those patient, spinning engines of gravity. But Hawking radiation is doing its slow work. Over 10 to the 67th power years, stellar mass black holes evaporate. Over 10 to the 100th power years, the supermassive monsters at the centers of dead galaxies follow. Each black hole, as it evaporates, pours its stored energy back into the universe as a faint spray of photons and other massless particles. And then, finally, there is nothing left. No matter, no structure, no mass. Only photons and gravitons, massless particles drifting through an infinite, expanding void. The universe has reached maximum entropy. It is smooth, featureless, and timeless. Because without massive particles, there are no clocks. Without clocks, there is no time. Without time, there is no scale. And without scale, the difference between infinite emptiness and a single, blazing point of energy ceases to exist. This is where Penrose's conformal rescaling takes hold. The infinite future of our aeon becomes the Big Bang of the next, not with a crunch, not with a bounce. With a mathematical transformation that preserves everything except size, and since size has no meaning in a universe without mass, nothing is lost. The aeon ends, the aeon begins, the cycle continues. Now, here is where this story takes a turn that changes everything. Because if the universe truly cycles through infinite aeons, if there is no beginning and no end to this sequence, then the implications for your existence are staggering. And they hinge on the very thing we discussed at the start, the Bekenstein bound. Remember, the number of possible arrangements of matter and energy in any finite region of space is finite. There is a ceiling, a hard cap, and if the universe cycles through an infinite number of aeons, each one containing a finite number of possible states, then eventually every possible arrangement must occur. Not once, not twice, but infinitely many times. Including the exact arrangement that constitutes you, your body, your brain, your memories, your consciousness. If consciousness is a product of physical arrangement, which everything we know about neuroscience suggests it is. This is not speculation. This is arithmetic. Finite states plus infinite time equals inevitable repetition. The same logic that guarantees a reshuffled deck of cards will eventually repeat applies to the particles that make up your body, your planet, your entire observable universe. Given enough aeons, the exact configuration that is you right now, reading this, thinking this, feeling this, will recur. It must. And this is where something remarkable happens. This idea, this conclusion that you have lived this exact life before and will live it again, is not new. It was proposed nearly a century and a half ago by a philosopher who had no access to quantum mechanics, no knowledge of black holes, no concept of the Bekenstein bound. He arrived at the same conclusion through sheer force of thought, reasoning from first principles about the nature of matter and time. His name was Friedrich Nietzsche, and he called his idea the eternal return. In the summer of 1881, while walking near a lake in the Swiss Alps beside a large pyramidal rock, Nietzsche was struck by what he later described as the most powerful idea of his life. He wrote it in his notebook in a kind of frenzy, not as a formal argument, but as a revelation. The idea was simple. If the amount of energy in the universe is finite, and if time is infinite, then every possible arrangement of that energy must eventually recur. Not approximately, exactly. Every joy, every sorrow, every moment of boredom and ecstasy, every breath and heartbeat and idle thought, all of it repeating forever. Nietzsche first shared this idea publicly in his 1882 book, The Gay Science. He presented it not as a scientific theory, but as a thought experiment, delivered by a demon who creeps into your loneliest moment and whispers, "This life, as you now live it and have lived it, you will have to live once more and innumerable times more. And there will be nothing new in it, but every pain and every joy and every thought and sigh must return to you, all in the same succession and sequence." What is staggering about this passage, written 8 years before Henri Poincaré published his famous recurrence theorem, is that Nietzsche's reasoning was essentially correct. Poincaré's theorem, published in 1890, proved mathematically what Nietzsche had intuited, that a conservative system confined to a finite volume will, given enough time, return arbitrarily close to any previous state. The philosopher had anticipated the mathematician, not through equations, but through an unflinching willingness to follow the logic of finitude and infinity to its end. But Nietzsche was not merely making a claim about physics. He was issuing a challenge. If this life will repeat exactly forever, what would that mean? Would you embrace it? Would you fall to the ground in despair? Or would you love it so fiercely that you would want nothing to be different, not forward, not backward, not in all eternity? This is what Nietzsche called amor fati, the love of fate. The idea that the highest possible affirmation of life is to will its eternal repetition. To say yes, not just to the good moments, but to every moment, every loss, every failure, every tedious afternoon, to want all of it again forever because it is yours. There is something deeply moving about the fact that this ancient intuition, this idea that was also held by the Stoics, the Pythagoreans, and the Hindu conception of the kalpas, the great cosmic cycles, has now found a possible foundation in the mathematics of modern physics. Penrose's CCC provides a mechanism by which the universe might actually cycle. The Bekenstein bound provides the finitude of states that makes repetition inevitable. And Poincaré's theorem provides the mathematical proof that return must occur, given sufficient time and a finite state space. But here is where intellectual honesty demands that we pause, because the story I have told you so far is the story that supports the idea of eternal return. And it is a beautiful story, but it is not the only story the physics tells. There are cracks in this picture, deep ones. And if we are going to take this journey seriously, we owe it to the truth to look at them. The first and most important crack is this. Penrose himself does not believe that CCC implies you have lived this exact life before. This is a crucial distinction that many people miss. In CCC, the universe cycles through aeons, yes, but Penrose has explicitly rejected the interpretation known as aeon monism, the idea that the end of our aeon loops back to its own beginning, creating a single, repeating loop. He considered this possibility and dismissed it, arguing that it would introduce causal paradoxes, situations where the future could influence the past in contradictory ways. In Penrose's own view, each aeon gives rise to a genuinely new aeon. Different initial conditions, different structures, different outcomes. The cycles continue, but they do not repeat. Now, Penrose is not the only voice on this question. In 2024, the philosopher of physics Baptiste Le Bihan published a paper arguing that aeon monism, the idea Penrose rejected, is actually a perfectly viable interpretation of CCC. Le Bihan argued that closed temporal loops do not necessarily produce paradoxes, as long as nothing within the loop changes. If everything happens exactly the same way each time, there is no contradiction. The past does not get altered. It simply recurs. Le Bihan's paper is carefully argued and philosophically rigorous, and it has reopened a debate that many assumed was settled. But it remains a minority position. The question of whether CCC implies identical repetition or merely sequential cycling is genuinely unresolved. The second crack comes from the physicist Sabine Hossenfelder, who has raised a pointed criticism of CCC that goes right to the heart of the repetition question. If the end of one aeon leaves an imprint on the beginning of the next, Hossenfelder argued, then each aeon inherits information from the previous one, and this inherited information would compound. Fluctuations from one aeon would produce larger fluctuations in the next, which would produce still larger fluctuations in the one after that. It is a positive feedback loop, and if such a loop exists, then the aeons are not repeating. They are diverging. Each one is more different from the last, not more similar. Under this view, the universe would not converge toward repetition. It would spiral outward into ever greater novelty. Penrose would need to explain why we find ourselves in a universe without these enormous accumulated fluctuations, and that explanation has not yet been fully provided. This does not disprove CCC, but it does introduce a tension that the theory must eventually resolve. The third crack is empirical. If CCC is correct, it should leave marks, fingerprints from the previous aeon, stamped onto the beginning of ours, and Penrose has proposed exactly what those fingerprints should look like. He calls them Hawking points. The idea is this. In the previous aeon, just as in ours, supermassive black holes would have been the last structures standing. As they evaporated through Hawking radiation, they would have released enormous amounts of energy concentrated at specific locations. When the aeon ended and the next one began, these concentrated bursts of energy would have been carried across the transition, stamped into the newborn universe like fossils in rock. And those fossils, Penrose argues, should be visible today. They should appear as anomalous hotspots in the cosmic microwave background, the ancient light left over from the Big Bang. In 2018 and 2020, Penrose and his collaborators Daniel Ahn, Krzysztof Meissner, and Paweł Nurowski published papers claiming to have found exactly these spots. They analyzed data from the Planck satellite and the WMAP probe and identified small circular regions in the cosmic microwave background where the temperature was anomalously high, with steep gradients around them. They reported these findings at a statistical confidence of 99.98%, a level that in many fields of science would be considered strong evidence, but other researchers were not convinced. The problem, they argued, was the look elsewhere effect. When you search a large dataset for any kind of pattern, you are bound to find some anomalies, simply by chance. The question is not whether anomalies exist, but whether they are more anomalous than you would expect from random noise. In 2020, a team led by Fiona Zhao and Douglas Scott reanalyzed the Planck data and found that the significance of the Hawking point signal dropped dramatically once this effect was accounted for. And in 2024, a team led by Eric Bodnier used a machine learning approach called Hawking Net to search for the same signals. Their conclusion was sobering. After removing unusually bright spots and accounting for statistical corrections, they found no significant evidence for Hawking points. The probability that the signal was real dropped to roughly 13%. Not impossible, but far from conclusive. Penrose and his team maintain that their analysis is sound and that the anomalies are real. The debate continues, but as of now, the strongest empirical prediction of CCC remains unconfirmed. This does not mean the theory is wrong. Many correct theories in physics took decades to find experimental support, but it does mean that we cannot yet point to the sky and say, there, that glow, that is the ghost of a black hole from before the Big Bang. There is another challenge, one that comes from deep within the mathematics of general relativity itself. In recent years, researchers have studied whether cyclic cosmological models can truly extend infinitely into the past. The question is whether you can trace the chain of aeons backward forever, or whether, at some point, the chain must have a beginning. A mathematical analysis found that many cyclic models are what physicists call geodesically past incomplete, meaning that the trajectories of particles, traced backward in time, reach a boundary beyond which they cannot be extended. In plain language, even cyclic universes may need a first moment, a true beginning, before which there were no aeons at all. The authors of this particular study noted that their analysis does not directly apply to Penrose's specific model, because in CCC, each aeon is infinitely larger than the one before, which changes the mathematics. But the broader point stands. The assumption of infinite past cycling is not automatic. It may be an additional assumption that requires its own justification. And finally, there is the challenge that comes from quantum mechanics itself. Even if the Bekenstein bound ensures that the number of possible states is finite, quantum mechanics introduces something that classical physics does not: genuine, irreducible randomness. When a quantum measurement is made, the outcome is not determined by any prior state of the universe. It is fundamentally probabilistic. This means that even if two aeons began in identical states, down to the last particle, the quantum events within them might unfold differently, not because of any hidden variable, not because of any missing information, but because quantum mechanics, at its deepest level, is random. If this is true, then even infinite time and finite states may not guarantee exact repetition. They would guarantee recurrence of macroscopic conditions, the broad strokes of galaxies and stars and planets. But the quantum details, the fine grain of which atom decays when, and which photon goes where, might always be different. And if consciousness depends on those fine details, then the question of whether you truly recur becomes far more subtle than the simple arithmetic of finite states and infinite time would suggest. These are not minor objections. They are deep, substantive challenges that any honest treatment of eternal return must face. And yet, even after facing them, the core of the argument remains standing, because the challenges do not disprove the possibility of recurrence. They complicate it. They add nuance and uncertainty. They turn a bold claim into an open question. But they do not close the door. And this is perhaps the most remarkable thing about the physics of eternal return. It is not a settled question. It is a living one. A question that sits at the intersection of general relativity, quantum mechanics, thermodynamics, and philosophy of mind. A question that the greatest minds of our era are still debating. Let us go deeper, because there is another mathematical result that bears directly on the possibility of recurrence. And it is one of the most elegant theorems in all of physics. It was proved in 1890 by the French mathematician Henri Poincaré, and it says something that seems almost too strange to be true. Poincaré's recurrence theorem states that a conservative dynamical system, one that conserves energy and is confined to a finite volume, will, given enough time, return to a state arbitrarily close to its initial state, not exactly identical, but as close as you like, as close as the width of an atom, as close as the diameter of a proton. For any degree of precision you specify, there exists a time after which the system returns to within that margin. The proof is surprisingly simple in its logic. If the system is confined to a finite volume and conserves energy, then its trajectory through the space of possible states is confined to a finite region. And a continuous trajectory in a finite space cannot wander forever without coming close to where it started. It is like a ball bouncing inside a box. No matter how chaotic the bouncing, the ball must eventually return near any point it has previously visited, not because the box is pushing it there, but because there are only so many places to go. The timescales involved are, to put it mildly, large. Boltzmann estimated that for a cubic centimeter of gas at room temperature, the recurrence time would be on the order of 10 to the 10 to the 19th power years. That is a number so vast that it dwarfs any other number in physics. The age of the universe at 13.8 billion years is essentially zero by comparison. The time for all black holes to evaporate, 10 to the 100th power years, is still essentially zero. The recurrence, time is not just long. It is long in a way that transcends any intuitive understanding of long. And yet, Poincaré's theorem guarantees that it is finite. The return will happen if the universe is truly a closed system with finite energy and finite volume, or if Penrose is right that the universe cycles through aeons each containing finite degrees of freedom, then recurrence is mathematically inevitable. The quantum version of this theorem has also been studied extensively. In quantum mechanics, the analog of Poincaré recurrence applies to systems with a discrete energy spectrum. The quantum state of such a system will return to within any specified distance of its initial state after a sufficiently long time. In 2018, researchers at the Vienna University of Technology provided experimental confirmation of quantum recurrence in a controlled system, watching a quantum state evolve and return to its original configuration with remarkable precision. But there is a subtlety here that matters enormously. In 2017, a theoretical analysis explored what happens when gravity is introduced into the picture. The researchers found that classical recurrence can be disrupted by the formation of black holes. When matter collapses into a black hole, the usual rules of phase-space dynamics are altered. Information that was previously accessible becomes trapped behind an event horizon. The system, in a sense, develops amnesia. This could quench classical recurrence, preventing the simple bouncing ball in a box picture from applying. However, the same researchers noted that quantum recurrence is more robust. Even black hole states subject to quantum evolution should eventually recur. The information is not truly lost. It is scrambled, encoded in the subtle correlations of Hawking radiation, and in principle, reversible. Whether this principle can be realized in practice, over the staggering timescales involved, remains an open question. But the mathematics is clear. Quantum mechanics does not forbid recurrence. It demands it, given the right conditions. So where does this leave us? We have a finite number of states, guaranteed by the Bekenstein bound. We have the possibility of infinite time, suggested by Penrose's CCC, and by the ongoing expansion of the universe. We have a mathematical theorem, Poincaré's, that guarantees return in any finite conservative system, and we have the quantum version of that theorem, which extends the guarantee to the microscopic realm. Together, these results form a chain of reasoning that leads to a startling conclusion. If the universe has a finite number of states, and if time extends without limit, then every configuration of matter and energy must recur, including the configuration that is you. Reading these words, breathing this breath, feeling whatever it is you are feeling right now, in this exact moment. But the chain has weak links. The if at the beginning of each statement is doing enormous work. If the number of states is truly finite, if time truly extends without limit, if quantum randomness does not prevent exact repetition, if CCC is correct, or if some other mechanism provides the infinite time needed. Each of these conditions is plausible, none of them is certain, and the gap between plausible and certain is, in physics, a chasm. Now, there is one more piece of this puzzle that we need to examine, and it is perhaps the strangest piece of all, because the logic of finite states and infinite time does not only predict that you will recur, it predicts something far more unsettling. It predicts that most observers in the far future of the universe will not be real people on real planets. They will be brains, disembodied, isolated, flickering briefly into existence out of the random fluctuations of a dead universe. They are called Boltzmann brains, and they are one of the most disturbing paradoxes in all of modern cosmology. The concept is named after Ludwig Boltzmann, the great Austrian physicist who, in the late 19th century, laid the foundations of statistical mechanics. Boltzmann understood that the second law of thermodynamics is not an absolute law. It is a statistical one. Entropy tends to increase not because it must, but because high entropy states are overwhelmingly more probable than low entropy states. There are simply far more ways for a room full of air molecules to be evenly distributed than to be clumped in one corner. So the air spreads out, not because a law forces it to, but because the odds are astronomical. But this statistical nature means that, in principle, entropy can decrease. It is fantastically unlikely, but not impossible, for all the air molecules in a room to spontaneously rush to one corner. And if you wait long enough, in a universe that has reached thermal equilibrium and has nothing but time, this will eventually happen. In fact, everything will eventually happen, including the spontaneous assembly out of random thermal fluctuations of a functioning human brain, complete with false memories of having lived an entire life on a planet that never existed. This is the Boltzmann brain, and the paradox it creates is devastating. Because if the universe reaches thermal equilibrium and then persists for an unimaginably long time, the number of Boltzmann brains that randomly fluctuate into existence will vastly outnumber the real observers who evolved naturally during the brief epoch of stars and planets. For every genuine person who lived a genuine life, there would be countless trillions of phantom brains, each one convinced that it is real, each one equipped with memories and sensations that feel as authentic as yours do right now. This means that if you take the statistics seriously, the odds are overwhelmingly against you being a real observer. You are far more likely to be a Boltzmann brain, a momentary flicker of consciousness in an otherwise dead universe, whose memories of the past are not records of real events, but random patterns assembled by chance. This is, to put it mildly, a problem. Because if you are a Boltzmann brain, then nothing you believe is reliable. Your memory of yesterday is not a memory. Your understanding of physics is not an understanding. Your belief that the universe began with a Big Bang, that it is 13.8 billion years old, that entropy increases over time, all of this could be a random fluctuation, a hallucination painted on the surface of a brain that popped into existence a fraction of a second ago and will dissolve back into chaos a fraction of a second from now. The physicist, Sean Carroll, has described this situation with characteristic clarity. The Boltzmann brain scenario, he argues, is cognitively unstable. It is a hypothesis that cannot simultaneously be true and justifiably believed. If you are a Boltzmann brain, you have no reason to trust any of your reasoning, including the reasoning that led you to conclude you are a Boltzmann brain. It is a logical trap, a serpent eating its own tail. This might sound like a quirky philosophical puzzle, but it has real consequences for physics. Any cosmological model that predicts more Boltzmann brains than real observers is, by this argument, self-undermining. It cannot be taken seriously as a description of reality because it destroys the very foundation of evidence and reasoning on which it rests. And this is where the Boltzmann brain paradox intersects with our larger story. Because many cosmological models, including some versions of eternal inflation and certain interpretations of the cosmological constant, do predict an abundance of Boltzmann brains. They predict a universe that, after a brief flowering of stars and life, settles into an eternal, dark epoch in which random fluctuations dominate. In January 2026, a new paper by David Wolpert, Carlo Rovelli, and Hartmut Scharnhorst, published in the journal Entropy, added a fresh twist to this debate. They argued that the standard Boltzmann brain arguments involve a subtle form of circular reasoning. The arguments assume that we can trust our memories and our understanding of physics to evaluate the probability of being a Boltzmann brain. But if the conclusion is that we probably are Boltzmann brains, then we cannot trust those very assumptions. Wolpert, Rovelli, and Scharnhorst showed that once you take this circularity seriously, the entire argument structure becomes far more fragile than it appears. The Boltzmann brain paradox, they suggest, may be as much a problem with our reasoning as it is with the universe. CCC has an interesting relationship with this problem. In Penrose's model, the far future of each aeon is not a static, eternal equilibrium. It is a transition. The universe does not sit in thermal death forever. Instead, it transforms. The end of one aeon becomes the beginning of the next, through the conformal rescaling we discussed earlier. This means that CCC, if correct, might avoid the Boltzmann brain problem entirely. The universe never lingers long enough in any single equilibrium state for phantom brains to accumulate. It cycles onward, always moving, always transforming. This is, in fact, one of the arguments in CC's favor. It sidesteps one of the most troubling paradoxes in modern cosmology. So let us step back and take in the full picture. We have climbed through layers of mathematics, physics, and philosophy. We have encountered the Bekenstein bound and the Poincaré recurrence theorem. We have walked through the life cycle of a universe, from the Big Bang to the evaporation of the last black hole. We have met Roger Penrose and Friedrich Nietzsche. We have grappled with the challenges to eternal return, from quantum randomness to the feedback problem. And we have stared into the abyss of the Boltzmann brain paradox and found it staring back. What emerges from all of this is not a simple answer. It is a question, the deepest, most personal question that physics has ever asked. If the universe cycles, if time is infinite, if your configuration will recur, then what does that mean for how you live right now? Nietzsche understood that this question is not merely intellectual, it is existential. It strikes at the heart of how you value your life. Because if this moment, this exact moment, will happen again and again, then it is not fleeting. It is eternal, not in some abstract metaphorical sense, but in the hardest, most literal sense that physics can provide. Every choice you make is a choice you will make forever. Every kindness is an eternal kindness. Every wasted afternoon is an afternoon wasted for all of time. Let us rest here for a moment. The mathematics has done its work. The arguments have been laid out. The evidence, both for and against, has been weighed. Now, let us simply sit with the idea and let it do what ideas of this magnitude are meant to do. Let it wash over you. Think about the cosmic microwave background, that ancient light that fills the sky in every direction. It is the oldest light in the universe, released just 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and for photons to fly free. This light has been traveling for 13.8 billion years. It has crossed the entire observable universe to reach you. And according to Penrose, embedded in that light are the faintest possible whispers of a universe that came before. Hotspots where ancient black holes breathed their last. Circular patterns where gravitational waves from a dying cosmos rippled through the birth of a new one. We may not yet be able to prove that those whispers are real. The data is ambiguous. The statistics are contested. But the possibility that the light touching your planet right now carries a message from before the beginning of time is one of the most extraordinary ideas in the history of human thought. And there are other hints. In 2024, a young researcher named Alexia Lopez, working at the University of Central Lancashire, discovered something that should not exist. She found a structure in the distant universe that is 1.3 billion light-years across. She called it the Big Ring. It is a vast, circular arrangement of galaxies, far larger than any structure that the standard model of cosmology allows. The theoretical limit for cosmic structures is about 1.2 billion light-years. The Big Ring exceeds that limit, and it was not alone. Lopez had earlier discovered another enormous structure, the giant arc, spanning 3.3 billion light-years. Both structures exist in the same region of the sky, at the same cosmic distance, separated by only about 12 degrees. These structures are a mystery. They violate what is known as the cosmological principle, the assumption that the universe, on the larger scales, looks the same in every direction. Structures this large should not form in a universe that is truly homogeneous. Something is making them. And Roger Penrose has suggested that the something might be echoes from a previous aeon. In his March 2025 paper, Penrose cited Lopez's discoveries as potentially supporting CCC. He noted that ring-shaped structures are exactly what you might expect to find if gravitational waves from the previous aeon had imprinted themselves on the matter distribution of our universe. Lopez herself has been in contact with Penrose. She visited Oxford to discuss her findings. And while the evidence is far from conclusive, the mere fact that anomalously large ring-shaped structures exist in the cosmos, structures that the standard model struggles to explain, is tantalizing. Now let us trace another thread, one we have touched on but not followed to its end. The history of this idea. Because the intuition that time curves back on itself is one of the oldest thoughts in human history, and tracing its lineage reveals something profound about the human mind, something about what we see when we look at the sky with enough patience. More than 2,500 years ago, in the Greek world, a philosopher named Empedocles taught that the cosmos oscillates between two forces, love, which draws things together, and strife, which tears them apart. Under love's influence, the elements merge into a perfect, undifferentiated sphere. Under strife's influence, they separate, forming the diverse world we know. And this oscillation, Empedocles believed, continues forever. The cosmos breathes in and breathes out, and neither the inhalation nor the exhalation is the first or the last. The Stoics took this further. They taught that the universe is periodically destroyed in an immense conflagration they called ekpyrosis, a great fire that consumes everything. And from the ashes, the universe is reborn in palingenesis, a new beginning that is identical to the old one. Every event recurs. Every person lives again. Every choice is made again, in exactly the same way. The Stoics debated whether the contents of each new universe were truly identical to the last, or merely so similar as to be indistinguishable. But the broad picture was clear. Time is a circle, not a line. This teaching was fiercely attacked by early Christian thinkers, particularly Augustine of Hippo, who saw in eternal return a denial of free will and the possibility of salvation. If everything repeats exactly, then nothing can be redeemed. There is no progress, no ultimate destination. Augustine argued passionately that time must be linear, that it must have a beginning and an end, and that the soul's journey through it must be unique and unrepeatable. The spread of Christianity through Europe effectively buried the idea of eternal return for more than 1,000 years. But the idea did not die. It lived on in other traditions. In the Hindu concept of the Kalpas, the great cosmic ages, each one lasting 4.32 billion years, the universe is created and destroyed in an endless cycle. Brahma, the creator god, is born from a lotus flower that springs from the navel of Vishnu, the preserver. Brahma creates the world and lives for 100 divine years, each divine day containing 1,000 great ages. And when Brahma dies, the universe dissolves back into Vishnu, and a new Brahma is born, and the cycle begins again. The timescales involved are staggering. A single life of Brahma spans 311 trillion years, and yet even that vast age is a single breath in the eternal rhythm of creation and dissolution. The Buddhist tradition holds a similar view, though with an important distinction. The cycle of samsara, the wheel of birth and death, applies not to the cosmos as a whole, but to individual beings. The goal is not to celebrate the cycle, but to escape it, to achieve nirvana, the cessation of suffering, and to step off the wheel forever. Yet the cosmic backdrop against which this individual journey unfolds is cyclical. The universe arises and falls, without beginning or end. These ancient traditions did not have the vocabulary of modern physics. They did not speak of entropy or conformal transformations or the Bekenstein bound, but they had the core insight that the universe is patient, that time is vast, and that endings are not what they seem. They sensed in their bones that the arrow of time might be an illusion, that the deepest truth is the circle, not the line. And then, in the 19th century, as physics began to grapple with the nature of heat and energy and the behavior of gases, the idea resurfaced in a new form. Ludwig Boltzmann, working in Vienna, was trying to understand how the second law of thermodynamics could emerge from the random motions of atoms. He succeeded brilliantly, showing that entropy is a measure of probability, that the tendency of systems to move toward disorder is simply a consequence of the fact that disordered states are overwhelmingly more numerous than ordered ones. But his success came with a troubling implication. If the universe is a closed system, and if it has been around forever, then it should have reached thermal equilibrium long ago. Everything should be the same temperature. There should be no stars, no planets, no people. The fact that we see structure, that we exist, that the universe is manifestly not in equilibrium, seemed to contradict the very laws that Boltzmann had helped establish. Boltzmann's response, developed with his assistant Ignaz Schutz in the 1890s, was ingenious and strange. Perhaps, he suggested, the universe as a whole is in equilibrium. Perhaps the vast majority of it is dead and featureless. But in rare random fluctuations, pockets of low entropy arise. Stars form, planets coalesce, life evolves. And for a brief moment, relative to the age of the cosmos, these pockets exist before entropy claims them once more. We, Boltzmann suggested, might be living in one of these fluctuations. The universe did not begin in a special state. It is simply that in an eternity of time, every state eventually occurs. This idea contained the seed of the Boltzmann brain problem we discussed earlier, and it also contained something else, a bridge, a connection between the ancient philosophical intuition of eternal return and the emerging mathematical language of statistical mechanics. Boltzmann, without knowing it, was building the scaffold that would eventually support Penrose's far more elaborate construction. Now let us turn to another aspect of this story that connects the abstract physics to something deeply personal. The question of memory. Because if the universe cycles, and if your configuration recurs, what happens to your memories? Are they preserved across aeons? Do you remember your previous lives in some deep, encoded physical sense? Or does each recurrence begin fresh, with the slate wiped clean? The answer, within the framework of CCC, is clear. Memories are not preserved across the transition between aeons. The conformal rescaling that connects the end of one aeon to the beginning of the next is not a process that carries specific information about individual structures. It carries the broad geometrical properties of space-time, the overall shape, the distribution of energy, the gravitational wave patterns, but the particular arrangement of atoms that constituted your brain, the specific neural connections that stored your memories of childhood, the synaptic patterns that encoded the sound of your mother's voice. These are not preserved. They are dissolved along with all other structures during the long, slow heat death of the aeon. This means that even if you recur, you do not remember having recurred. Each life is experienced as if it were the first. Each wonder is fresh. Each loss is new. There is no accumulation of wisdom across aeons, no gradual enlightenment, no sense of déjà vu that stretches across cosmological time. Each time you live this life, you live it with the same innocence and the same ignorance as the first time. If there was a first time, this might seem disappointing. If you cannot remember your past lives, what difference does it make that they occurred? But consider the alternative. Consider what it would mean to remember, to carry with you, in some deep layer of consciousness, the weight of trillions of identical lifetimes. Every joy experienced not just once, but an infinity of times. Every sorrow felt not just in this life, but across the entire history of the cosmos. The weight would be unbearable. The freshness would be gone. Each experience would be dulled by the infinite repetition that preceded it. And perhaps the forgetting is not a flaw in the design, but a feature, a reset, a cleansing. The universe wiping the slate so that the next performance can be experienced with full intensity. Not a cruel trick played on an unwitting consciousness, but a gift, the gift of beginning again without the burden of having begun before. Nietzsche understood this too. His demon does not tell you that you will remember your past lives. The demon tells you that you will live this life again. The emphasis is on the living, not the remembering. The challenge is not to recall the repetition, but to embrace it. To live this life so fully and so well that you would want it to repeat exactly as it is forever. Not because you will know it is repeating, but because the quality of the life itself is its own justification. Now let us follow another thread, one that takes us from the scale of the universe down to the scale of atoms. Because the physics of eternal return is not only a story about cosmology, it is a story about information, about what it means for a physical system to contain a pattern, to encode a structure, to hold within its arrangement of particles the ghostly blueprint of something as complex and fragile as a human mind. When Stephen Hawking first showed that black holes emit radiation and slowly evaporate, he created what became known as the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. Every process in nature is, in principle, reversible. If you know the complete quantum state of a system, you can predict its future and reconstruct its past with perfect accuracy. Information is conserved, just as energy is conserved. It is a fundamental law. But when something falls into a black hole, that information seems to disappear. The object crosses the event horizon and is lost to the outside universe. And when the black hole eventually evaporates through Hawking radiation, the radiation it emits is thermal. It is random. It carries no obvious imprint of what fell in. The information, it seems, has been erased. Over the years, most physicists have come to believe that information is not truly lost in black holes. Instead, it is encoded in subtle correlations within the Hawking radiation, correlations so faint and so complex that they are, for all practical purposes, unreadable, but that are in principle sufficient to reconstruct everything that fell in. This view has been supported by theoretical work in string theory and by the holographic principle, which suggests that all the information contained within a volume of space can be represented on its boundary. The 2023 discovery that Hawking radiation arises from curved space-time in general, not just from black holes, added another layer. If all massive objects emit a form of this radiation, then the universe as a whole is slowly dissolving its structures into radiation. And if the information contained in those structures is preserved in the radiation, then nothing is ever truly lost. The universe is not erasing its history. It is translating it, converting it from one form to another, from organized structures to diffuse radiation, but preserving the content all the while. This has profound implications for the possibility of recurrence. If information is conserved, then the total state of the universe is always determined by its previous states. The chain of causation is unbroken. And if the state space is finite, then the conservation of information combined with the finiteness of states and the infinity of time creates the conditions for recurrence with even greater force. The pattern that is you is not merely a shape in space. It is a thread in the informational fabric of the cosmos. And that thread, if the physics is right, cannot be cut. Let us consider one more dimension of this story. The question of what it means to be here now, in a universe that may be eternal. Because beyond the mathematics and the physics, beyond the theorems and the data, there is the lived experience, the feeling of being a conscious creature in a vast, ancient, possibly infinite cosmos. And that feeling deserves its own attention. Consider the sheer improbability of your existence, not in the metaphorical sense, in the physical, quantifiable sense. The odds against any particular arrangement of atoms producing a conscious being are astronomical. The number of possible configurations of the matter in your body vastly exceeds the number of configurations that would produce anything resembling a working brain. You are not merely unlikely. You are, from the perspective of statistical mechanics, essentially impossible. And yet, here you are. This improbability is not something to be explained away. It is something to be marveled at, because it tells you something about the universe you live in. It tells you that the universe is not merely large, it is creative. It has, through the blind processes of physics and chemistry and biology, assembled from carbon and hydrogen and oxygen and iron, a structure capable of wondering about its own existence. The universe has built a mirror and is looking at itself. The carbon in your bones was made in the core of a red giant star that lived and died billions of years before our solar system formed. The iron in your blood was forged in the cataclysmic explosion of a supernova, an event so violent that it briefly outshone an entire galaxy. The hydrogen in the water in your cells has been around since the first 3 minutes after the Big Bang. You are, quite literally, made of the universe, not a resident of it, not a visitor, an expression of it, a way the cosmos has found to know itself. And if Penrose is right, this is not the first time the cosmos has known itself through you, and it will not be the last. You are a note in an infinite symphony, a wave in an ocean that has no shore, a thought that the universe keeps thinking over and over because it is too beautiful to think only once. The ancient Stoics believed something very similar. They called the great cycle of cosmic destruction and rebirth ekpyrosis and palingenesis, the world consumed by fire and born again from the ashes. The Pythagoreans, centuries before Christ, taught that after certain specified periods, the same events occur again, and that nothing was entirely new. These traditions did not have the mathematics of Poincare or the cosmology of Penrose, but they had the intuition, the sense that the universe is too vast and too patient for anything to happen only once. Whether this intuition is correct in the precise mathematical sense that modern physics demands remains to be seen. The Hawking point evidence is inconclusive. The aeon monism debate is unresolved. The role of quantum randomness in preventing exact recurrence is still being explored. The feedback problem that Hossenfelder raised has not been answered. These are real challenges, and they deserve real attention. But the possibility, the sheer, staggering possibility. That is what makes this one of the most beautiful ideas in the history of human thought. Not the certainty, the possibility. The idea that the universe may be an eternal return, cycling without end, creating and dissolving, burning and being born, with you at the center of every cycle, living this exact life in this exact moment, forever. There is a particular quality to the darkness between stars. It is not empty. This is something that surprises most people when they first learn it. The space between stars, the space between galaxies, the vast stretches of apparent nothing that dominate the visible universe are not nothing at all. They are filled with radiation, with magnetic fields, with the faintest possible whisper of energy that pervades every cubic centimeter of existence. Even in the deepest void, far from any star or galaxy, the temperature of space is not zero. It is 2.7 degrees above absolute zero. The entire universe is bathed in a glow so faint that no human eye could detect it, but so pervasive that it fills every direction you could possibly look. This glow is the cosmic microwave background, and it is the oldest light in the universe. When the universe was very young, less than 400,000 years old, it was a dense, opaque fog of hot plasma. Electrons and protons were moving so fast that they could not hold together to form atoms. Photons, particles of light, could not travel more than a short distance before colliding with a free electron and being scattered in a random direction. The universe was bright, but it was also blind. No light could travel in a straight line. No signal could propagate. It was as if the entire cosmos were made of glowing fog. Then, as the universe expanded and cooled, something remarkable happened. The temperature dropped below about 3,000 degrees, and at that temperature, electrons slowed down enough to be captured by protons. Atoms formed. Hydrogen atoms mostly, with a smattering of helium. And suddenly, for the first time, the universe became transparent. The photons that had been bouncing around in the fog were released. They streamed outward in every direction, carrying with them a snapshot of the universe as it was at that moment, 380,000 years after the Big Bang. Those photons are still traveling. They have been traveling for 13.8 billion years, and they have been stretched by the expansion of the universe from visible light to microwaves. What was once a blinding white glow is now a faint hiss of radiation, detectable only by sensitive instruments. But it is everywhere. It is in this room. It is passing through your body right now. Dozens of photons from the dawn of time threading through the spaces between your cells, with every passing second. This is the canvas on which Penrose believes the signatures of a previous aeon are written. The search for these signals has been one of the most closely watched efforts in modern cosmology. It is a search that carries enormous stakes. If Hawking points are found, confirmed, and accepted by the broader community, it would be among the most important discoveries in the history of science. It would mean that our Big Bang was not the beginning, that there was a before, that the universe has a history deeper than 13.8 billion years, deeper potentially than any finite number could express. And if they are not found, if the anomalies turn out to be statistical noise, then CCC loses its strongest empirical anchor. It does not die, because theoretical elegance and mathematical consistency count for something in physics, but it becomes harder to distinguish from a beautiful guess. This is how science works, not with sudden revelations and clean answers, but with painstaking, incremental, sometimes frustrating progress. The truth does not announce itself. It hides, and it must be coaxed out through careful measurement and honest analysis. And sometimes the truth takes decades to emerge. The cosmic microwave background itself was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who initially thought the faint hiss they detected was caused by pigeon droppings on their antenna. It took years for the scientific community to fully appreciate the significance of their discovery. And it took decades more for satellite missions like COBE, WMAP, and Planck to map the CMB with enough precision to reveal the subtle fluctuations that tell us about the first moments of the universe. The search for Hawking points is in its early stages. Better data will come, more precise measurements, more sophisticated statistical tools, and perhaps in time, a clear answer. But for now, we live in the ambiguity, and there is a kind of beauty in that too, in not knowing, in standing at the edge of a question so large that the entire scientific enterprise is barely adequate to it. Now let us consider something that connects all of these ideas to the question of how the universe began its current aeon. One of the deepest mysteries in cosmology is the problem of initial conditions. Why did the Big Bang produce a universe that was so extraordinarily smooth and uniform? The early universe was almost perfectly homogeneous. The temperature of the cosmic microwave background is the same in every direction, to within 1 part in 100,000. This uniformity is astonishing, because different regions of the early universe were so far apart that light had not had time to travel between them. They had no way of communicating with each other, no way of equalizing their temperatures, and yet they were at the same temperature. Standard cosmology solves this puzzle with inflation. The idea, proposed by Alan Guth in 1981, is that the universe underwent a brief period of exponential expansion in its first fraction of a second. This expansion stretched a tiny, causally connected region to a size much larger than the observable universe, explaining why everything we see looks so uniform. The quantum fluctuations present before inflation were also stretched, becoming the seeds of the galaxies and clusters we see today. Inflation has been remarkably successful as a theory. Its predictions match the observed pattern of fluctuations in the CMB with impressive precision. But Penrose has long been a critic of inflation. He argues that inflation does not truly solve the problem of initial conditions. It merely pushes it back a step. For inflation to work, the universe must start in a very specific state, one that is smooth enough and energetic enough for the inflationary process to begin. And explaining why the universe was in that state requires either additional assumptions or an appeal to the kind of fine-tuning that inflation was supposed to eliminate. CCE offers a different answer. The smoothness of the Big Bang is not a mystery to be solved. It is a natural consequence of the conformal rescaling from the previous aeon. The heat death of the previous ion, in which all structure was erased and entropy was maximized, becomes the smooth, uniform beginning of the next. The low entropy of the Big Bang is inherited from the high entropy of the previous aeon's far future, because Penrose's Weyl curvature hypothesis ensures that the gravitational degrees of freedom, which dominate the entropy budget of the universe, are reset at the transition. The universe starts smooth because the transition demands it. This is an elegant solution, and it is testable, at least in principle. If CCC is correct, the signatures it leaves in the CMB should be different from those predicted by inflation. The concentric circles and Hawking points that Penrose proposes are not features of inflationary cosmology. If they are found and confirmed, they would favor CTC over inflation. And if they are not found, they would favor inflation over CCC. The two theories make different predictions, and the data, eventually, should distinguish between them. Penrose has also pointed to another type of evidence. His Weyl curvature hypothesis, which is a key component of CCC, makes a specific prediction about the geometry of the Big Bang. It predicts that the Weyl curvature tensor, which measures the tidal gravitational forces in spacetime, should vanish at the Big Bang. This is a mathematical statement about the shape of spacetime at the moment of creation. It implies that the Big Bang was not a chaotic, random explosion, but a geometrically precise event, smooth and ordered in a very specific way. This prediction is consistent with what we observe, but it has not yet been tested with the precision needed to confirm or rule out CCC specifically. The story of CCC is, in many ways, the story of a single mind pushing against the boundaries of accepted wisdom. Penrose is not a young rebel. He is a 90-something-year-old Nobel laureate who has earned the right to be listened to, even when his ideas are controversial. And his ideas are controversial. Most working cosmologists do not accept CCC. They find the evidence for Hawking points unconvincing. They are skeptical of the assumption that all massive particles must eventually decay. They worry about the lack of a detailed physical mechanism for the transition between aeons. And yet, CCC will not go away. It keeps producing new predictions, new papers, new connections to observed phenomena. The 2025 paper with Meissner, introducing the gravitational wave epoch, showed that the theory is still being developed and refined. The connection to Lopez's big ring and giant arc structures opened a new observational avenue. And the philosophical implications explored by Le Bihan and others continue to generate interest among philosophers of physics. This is how science advances, not by unanimous agreement, but by the patient, persistent exploration of ideas that refuse to die. Einstein's general relativity was controversial for decades. Quantum mechanics was resisted by some of its own creators. The Big Bang itself was dismissed by many physicists, including Fred Hoyle, who coined the term as a derisive joke. The history of physics is littered with ideas that were once considered outrageous and are now considered obvious. Whether CCC will join that list remains to be seen, but the mere fact that it is being taken seriously, debated, tested, and refined by working scientists is a testament to the power and elegance of Penrose's original vision. The evening is growing deep. The stars are shining. And you have been holding in your mind, for quite a long time now, an idea of extraordinary weight and beauty. Let us begin to draw the threads together. Here is what we know, as firmly as physics can know anything. The universe began in a state of very low entropy. It is expanding. It will continue to expand. The stars will die. The black holes will evaporate. And the far future, barring something completely unexpected, will be a vast, cold, empty space filled with nothing but the faintest radiation. Here is what we believe, tentatively, provisionally, with the appropriate degree of scientific humility. The universe may cycle. Time may be infinite. Your configuration may recur. But we do not yet have proof. We have possibilities. We have mathematics. We have hints in the data. And we have the ancient, persistent, cross-cultural intuition that endings are not what they seem. And here is what we feel. The deep, quiet feeling that comes from contemplating these ideas with honesty and openness. A feeling that is part awe, part vertigo, part peace. The feeling of standing at the edge of the knowable and looking out into the vast, dark, beautiful unknown. You are, whether you like it or not, a cosmological being. Your existence is intertwined with the fate of the universe, Your identity is a question that cannot be separated from the question of what happens when the last star goes out. And your future, if you have one beyond this life, is written not in any sacred text, but in the equations of general relativity and quantum mechanics. The night is deep now. The stars are shining. Some of them are already dead, their light still traveling, a message from the past that will arrive in the future and be seen by a consciousness that exists in the present. This is how light works. It stitches together past and present and future into a single fabric. It connects what was to what is to what will be. And in CCC, it is light, photons, massless and timeless, that carries the universe across the boundary between aeons. Light is the bridge. Light is the thread. Light is the thing that does not end when everything else does, because light, traveling at the speed of light, does not experience time. For a photon, the death of a universe and the birth of the next happen in the same instant. There is no gap, no pause, no darkness between. Perhaps that is the most beautiful image in all of this. The image of light, undying, infinite, weaving its way through aeon after aeon, carrying the shape of the cosmos with it, preserving the geometry, the angles, the relationships, even as the scale changes beyond all recognition. The universe dies, and the light survives. The universe is reborn, and the light is there, already, carrying the seeds of everything that will follow. You are part of that light now, not metaphorically, physically. The photons that bounce off your skin and travel outward into space carry information about you, your shape, your temperature, the color of your eyes. These photons will travel for billions of years, stretching and cooling as the universe expands, until they too become part of the cosmic background, part of the ancient glow, part of the message that one aeon sends to the next. Your light will be there in the background when the next aeon begins, faint, diluted beyond any possible detection, but there, a part of the initial conditions, a whisper in the static, a ghost in the glow. And from those initial conditions, from the subtle patterns in the radiation, from the gravitational wave echoes and the temperature fluctuations and the geometry of the crossover surface, a new universe will emerge. Stars will form. Galaxies will spin. Planets will cool. And somewhere, on one of those planets, in one of those galaxies, a particular arrangement of carbon and hydrogen and oxygen and iron will come together. Neurons will connect. Synapses will fire. Memories will form. And a consciousness will arise that feels exactly like yours, that thinks exactly like yours, that wonders on a quiet evening whether it has been here before, and it will not know the answer, just as you do not know the answer now. It will lie in the darkness looking up at unfamiliar stars and feel the same pull that you feel, the same tug of recognition, the same inexplicable sense that the universe is trying to tell you something. Something about time, something about light, something about the strange, beautiful, possibly eternal nature of being alive. The universe does not owe you this. It does not owe you comfort or meaning or the assurance that your life matters in any cosmic sense. It simply is. And it is stranger and more beautiful than anything you could invent. But you can listen. You can pay attention. You can take the facts as they are, the mathematics as it is, the evidence as it stands, and you can sit with them, not to extract a moral or a lesson or a takeaway, but to feel the shape of the question. To let it resonate in you, the way a bell resonates in the air, not because the air understands the bell, but because resonance is what happens when two things share the same frequency. You and the universe share a frequency. You are made of its matter. You are subject to its laws. You are shaped by its history, and you will be dissolved by its future. And in between, in this brief, luminous interval between your beginning and your ending, you have the extraordinary privilege of knowing that you exist, of wondering why, of lying still on a quiet evening and thinking about black holes and aeons and the eternal return. That privilege is not diminished by the possibility that it will recur. If anything, it is deepened, because if this moment is eternal, then the privilege is eternal too. The wonder is permanent. The awe does not fade. It echoes on and on through the cycling of the cosmos, preserved not in memory but in structure, in the pattern, in the arrangement of atoms that gives rise to the thought, I am here. So as you drift now, as the weight of the day lifts and the darkness settles in, carry this thought with you, not as a burden, not as a riddle to be solved, but as a kind of lullaby. The universe may be infinite, your life may be eternal, and this moment, this quiet, unremarkable moment, may be the most permanent thing there is. The ancient light is still streaming, the cosmos is still expanding, and you, improbable, beautiful you, are still here, as you have always been, as you may always be. Let the stars hold you. Let the silence speak. And let the deepest part of your mind, the part that has always suspected that there is more to time than what the clock shows, let that part rest now. You have travelled far tonight, from the Bekenstein bound to the evaporation of black holes, from Penrose's aeons to Nietzsche's demon, from the hot spots in the cosmic microwave background to the quiet question of what it means to live a life that might last forever. There is nothing more to prove, nothing more to argue, only this: the universe is vast, time may be infinite, and you are made of the same stuff as the stars that burn in the deep. The atoms that form your thoughts were once inside those stars, and when those atoms scatter, as they will join the great cycle once more. Drifting through the void, pulled by gravity, shaped by chance, until the conditions are right, and the pattern forms again, and somewhere, somewhen, in an aeon that has not yet begun, you open your eyes, and you wonder, as you have always wondered, what it all means. Rest now. The universe will wait. It always does. The stars are patient. They burn for billions of years without complaint, converting hydrogen to helium, helium to carbon, carbon to oxygen, building the elements that will one day become planets and oceans and the bones of living things. They do not rush. They do not worry about running out of time. They simply burn, steadily, faithfully, for as long as the fuel lasts. And when the fuel runs out, they do not vanish. They transform. They become white dwarfs or neutron stars or black holes. They become something else. Something that endures in a different form, for a different span of time, serving a different purpose in the great economy of the cosmos. You are like that. You burn, not with nuclear fusion, but with the slower, gentler fire of metabolism. The chemical reactions in your cells, the electrical impulses in your nerves, the steady rhythm of your heart, these are your fusion, your way of converting matter into energy, energy into motion, motion into thought. And when your fuel runs out, as it will, you too will transform. The atoms that made you will not disappear. They will scatter. They will be taken up by other processes, other systems, other forms. They will become soil and air and water and eventually new stars. And if CCC is right, they will become you again. Not in some vague poetic sense, in the most literal physical sense possible. the same atoms or atoms exactly like them, arranged in exactly the same way, producing exactly the same thoughts, in exactly the same order, in an aeon so far from this, one that the distance between them cannot be expressed in any number that has a name. This is the weight of the idea. This is what Nietzsche felt when the demon whispered in his ear. This is what the Stoics meant when they spoke of palingenesis. This is what the Hindu sages meant when they described the breathing of Brahma. Not a metaphor, not a wish, a possibility, grounded in the deepest physics we have. A possibility that, even if it can never be proven, can never quite be dismissed. And so we end where we began, with you, lying here, breathing, existing. A temporary arrangement of ancient matter, held together by forces that are older than the earth, powered by reactions that are older than the sun, thinking thoughts that are, in the grand scheme of things, extraordinarily new. You are the universe's latest thought, its freshest experiment, its newest way of knowing itself. And if the universe is an eternal return, then you are also its oldest thought, its first experiment, its most enduring way of knowing itself. You have always been here. You will always be here, not because you are special, but because the mathematics is relentless and the universe is patient, and given enough time, everything that can happen will happen, and everything that has happened will happen again. But before we say goodnight, let us linger a little longer, because there are still quiet corridors of this idea that we have not walked through. And some of them contain the kind of stillness that makes the journey worth taking. Let us think about what it means for the universe to forget its size. This is the central trick of CCC, the sleight of hand that makes the whole thing work, and it deserves more attention because it is one of the strangest ideas in modern physics. In everyday life, size matters. A mountain is different from a pebble. A galaxy is different from a grain of sand. We take for granted that the universe has a definite scale, that there is a meaningful difference between large and small, between near and far, between the width of an atom and the diameter of the observable universe. And for most of the universe's history, this is correct. The existence of massive particles, particles with rest mass, provides a natural ruler. The mass of an electron, for instance, defines a length scale through its Compton wavelength. As long as massive particles exist, the universe has a built-in yardstick. It knows how big it is. But in the far, far future, after all massive particles have decayed, after the last black hole has evaporated, the universe loses its yardstick. There are no more rulers, no more clocks, only photons and gravitons, massless particles that travel at the speed of light and do not experience the passage of time. For these particles, all distances are equivalent. All durations are the same. The concept of scale, so fundamental to our everyday experience, simply ceases to apply. This is not a metaphor. It is a precise mathematical statement about the structure of space-time. In the language of differential geometry, the space-time of the far future becomes conformally flat. Its geometry is determined entirely by the angles between light rays, not by the distances between points. And a conformally flat space-time can be smoothly mapped onto the geometry of a Big Bang, because the Big Bang too is conformally flat. The shapes match, the angles align. The only thing that differs is the scale, and scale has lost its meaning. Penrose saw this, and he recognized it as something extraordinary. Not just a mathematical curiosity, but a physical mechanism, a way for the universe to genuinely transition from one state to another without any discontinuity, without any boundary, without any moment at which this aeon ends and the next aeon begins. The transition is seamless. From the perspective of the massless particles that carry the universe through it, nothing happens. They simply continue, as they always have, traveling at the speed of light through a space-time whose geometry has changed, but whose essential structure, its conformal structure, has been preserved. This is the Weyl curvature hypothesis at work. Penrose proposed, as part of CCC, that the Weyl curvature tensor, which measures the tidal distortions of space-time caused by gravity, must vanish at the beginning of each aeon. This is what ensures that each Big Bang is smooth and uniform, rather than chaotic and lumpy. It is a strong constraint, and it is one that the observed universe appears to satisfy. The early universe, as revealed by the cosmic microwave background, was extraordinarily uniform. The Weyl curvature was very close to zero. This is consistent with Penrose's hypothesis, though it is also consistent with inflation, which makes a similar prediction through a different mechanism. The key difference is this. In inflationary cosmology, the smoothness of the early universe is produced by a brief period of exponential expansion that stretches out any initial irregularities. The universe starts rough and is smoothed by inflation. In CCC, the smoothness is inherited from the previous aeon. The universe starts smooth because the transition demands it. The cause of the smoothness is not a process within the universe, but the geometry of the connection between ions. This is a profound conceptual difference. In one picture, the universe smooths itself out through a physical process. In the other, the smoothness is a boundary condition, a property of the transition itself. Both pictures are consistent with the data, and distinguishing between them may require observations that we do not yet have the technology to make. Let us also consider something about the nature of time itself. Because CCC does not merely propose that the universe cycles, it proposes something far more radical. It proposes that our intuitive understanding of time as a quantity that flows uniformly from past to future, that has a definite beginning and possibly a definite end, is incomplete. In CCC, time is not a line. It is not even a circle. It is something more like a spiral or a helix, or perhaps something that has no analogy in everyday experience at all. Within each aeon, time flows as we understand it, from the Big Bang forward, through the era of stars and galaxies, through the long dark age of black hole evaporation, to the far future of photons and gravitons. But at the boundary between aeons, time undergoes a transformation. The future infinity of one aeon is identified with the initial singularity of the next. This identification is not temporal in the usual sense. It is conformal. It preserves the structure of light cones, the fundamental building blocks of causal relationships in space-time, but it does not preserve the scale of time. 1 billion years in the far future of one aeon and a trillionth of a second after the Big Bang of the next aeon are, conformally, the same thing. This means that the transition between aeons is not something that happens in time. It is something that happens to time. It is a change in the very structure of temporal experience, and it raises a question that physics, at present, cannot answer. What does it feel like to be at the boundary? Is there a subjective experience of the transition? Or is the transition something that can only be described from the outside, from the perspective of the mathematics, and not from the inside, from the perspective of a conscious being? The answer, almost certainly, is that there is no subjective experience of the transition, because there are no conscious beings at the transition. Consciousness requires complexity. It requires neurons and synapses, and the intricate, delicate architecture of a biological brain. And at the boundary between aeons, no such architecture exists. There are only photons and gravitons, the simplest possible particles, carrying the simplest possible information. The transition is not experienced, it simply occurs, like the changing of the seasons on an uninhabited planet, like the rotation of a galaxy with no one to watch it turn. But the fact that the transition is not experienced does not mean it is not real. The universe does not need an audience. It does not perform for the benefit of conscious observers. It simply evolves, according to its laws, through states that are sometimes complex enough to support consciousness, and sometimes not. The aeons with stars and galaxies and brains are the exception, not the rule. The vast majority of the universe's history, measured in terms of time, is dark and empty and unconscious. The brief periods during which minds exist, during which the universe knows itself through the wondering of sentient beings, are islands of light in an ocean of silence. And yet, those islands are the whole point, not from the universe's perspective, because the universe has no perspective, but from ours. From the perspective of the beings who exist on those islands, who look up at the sky and wonder what it all means, who build telescopes and write equations and argue about the nature of time, who lie awake at night, as you are doing now, and feel the strange, aching beauty of being conscious in a cosmos that may be infinite. This is what Roger Penrose has given us. Not certainty, not proof, but a framework within which to think about the biggest questions there are. A framework that takes the deepest mathematics, the most careful observations, and the most rigorous logic, and applies them to questions that have haunted human beings since the first time someone looked at the stars and wondered whether they would always be there. The framework is incomplete. It has gaps and challenges and unresolved tensions. It may, in the end, turn out to be wrong. Many beautiful theories in physics have turned out to be wrong. But even wrong theories can illuminate the truth by showing us where the boundaries of our knowledge lie, and by pointing us toward the questions we need to ask next. And the questions that CCC raises are among the most important in all of science. Does the universe cycle? Is time infinite? Can the far future of one cosmos become the infancy of the next? Are there ghosts of ancient black holes hiding in the oldest light? Is the uniformity of the early universe a clue to what came before? These are not idle speculations. They are precise mathematical questions with precise mathematical answers that we do not yet have. And the search for those answers is one of the great ongoing adventures of the human mind. Let us think now about what all of this means for the feeling you have right now, in this moment. The feeling of being alive, of being aware, of being a particular person, in a particular place, at a particular time, with particular memories and particular hopes and particular fears. This feeling, whatever it is produced by the arrangement of matter in your brain, by the specific pattern of electrical and chemical activity that constitutes your conscious experience. It is, as far as we can tell, a physical process. It emerges from the laws of physics in the same way that the orbit of a planet emerges from the laws of gravity, or the flow of a river emerges from the laws of fluid dynamics. It is natural, it is lawful, and it is, in the grand scheme of things, extraordinarily rare. Most of the matter in the universe does not think. Most of the matter in the universe does not feel. Most of the matter in the universe is hydrogen gas, drifting through the void, or iron at the core of a dead star, or photons streaming through the emptiness between galaxies. Consciousness, as far as we can tell, requires a very specific kind of arrangement, an arrangement that is complex enough to process information, flexible enough to model the external world, and self-referential enough to generate the experience of being a self. This arrangement exists on Earth. It may exist on other planets, in other solar systems, in other galaxies. It may have existed in previous aeons, and it may exist in future ones. But it is not the default. It is the exception. And the fact that it exists at all, that the universe has produced, through billions of years of blind, undirected physical processes, a structure capable of wondering about its own existence, is perhaps the most astonishing fact in all of science. If eternal return is true, then this astonishing fact is not a one-time accident. It is a recurring feature of reality. Consciousness is not a spark that flickers once and goes out. It is a flame that the universe keeps lighting over and over, in aeon after aeon, because the conditions for its emergence are contained within the finite state space of the cosmos, and the infinite cycling of time guarantees that those conditions will be met again and again. This is a strange kind of immortality, not the immortality of a soul that persists through time, unchanged and unchanging, but the immortality of a pattern that recurs. A pattern that is erased and rewritten, destroyed and rebuilt, forgotten and remembered, in an endless cycle that has no beginning and no end. You are not immortal in the way that religions promise. You are not preserved. You are not saved. But you are, perhaps, inevitable. A pattern that the universe cannot help but produce, given enough time and enough shuffling of its finite deck of cards. And there is something both humbling and exalting about that. Humbling, because it means you are not unique in the way you might have thought. There may be trillions of versions of you, scattered across the aeons, each one living the same life, each one unaware of the others. Exalting, because it means you are woven into the fabric of reality in a way that goes beyond anything you could achieve through your own efforts. You are not just a person. You are a recurrence, a theme, a motif in the music of the cosmos. Let us think about what the universe looks like from the outside, if there is an outside. If CCC is correct, the universe is an infinite sequence of aeons, each one expanding from a big bang to a heat death, each one giving way to the next through a conformal transformation. From the outside, if such a perspective were possible, this sequence might look like an infinite chain of beads on a string, each bead a complete universe, each connection a boundary, where the physics of one bead matches the physics of the next. Or it might look like a single thread, spiraling outward forever, each loop a complete aeon, the thread never crossing itself, never knotting, just spiraling endlessly through a space that has no boundary and no center. Or, if Le Bihan's aeon monism is correct, it might look like a single loop, a circle, the end connected to the beginning, the universe biting its own tail like the ancient symbol of the Ouroboros, the serpent that devours itself and is reborn from itself in an eternal cycle of death and renewal. We do not know which picture is correct. We may never know. The question of whether the aeons are many or one, whether the sequence has a beginning or is truly infinite, whether the future of our aeon connects to the past of a different aeon or to its own past, these are questions at the very edge of what physics can address. They may require a theory of quantum gravity, a theory that reconciles general relativity with quantum mechanics before they can be answered, and we do not yet have such a theory. But the fact that we can ask the questions, that we can formulate them precisely, that we can identify what observations would be needed to answer them, is itself a remarkable achievement. A century ago, the idea that the universe had a beginning was considered radical. Half a century ago, the idea that the universe would expand forever was considered speculative. Today, both are accepted as well-supported conclusions of observational cosmology. The questions we are asking now about what came before the Big Bang, about whether the universe cycles, about whether time is infinite, may seem equally radical and speculative, but they are grounded in the same tradition of mathematical rigor and empirical testing that has carried cosmology from the margins of philosophy to the center of science. There is a lesson in this. A lesson about patience. About the willingness to ask questions that cannot yet be answered, to explore ideas that cannot yet be tested, to hold open the door to possibilities that the next generation, or the generation after that, may finally be able to walk through. Science is a relay race. Each generation carries the baton a little further, sees a little more clearly, understands a little more deeply, and the questions we leave behind, the unanswered questions, the open questions, the beautiful, maddening, irresistible questions, are not failures. They are gifts. They are the invitations we leave for those who come after us. The invitation to keep looking, keep wondering, keep asking what happens next. And in a universe that may cycle forever, what happens next is the most important question there is. Because next may not mean the end. It may mean the beginning. The end of the stars may be the beginning of the photons. The end of the photons may be the beginning of the next aeon. The end of the next aeon may be the beginning of the one after that. And somewhere, in that long chain of beginnings and endings, your pattern recurs. Your consciousness reignites. Your eyes open. And you wonder, once again, as you have always wondered, what it all means. The wondering is the point, not the answer. The wondering. Now let us return one last time to the man at the center of this story, Roger Penrose. In his 90s, still publishing, still arguing, still pushing the boundaries of what physics can tell us about the universe. A man who has spent his entire life at the intersection of mathematics and reality, who sees in the equations of general relativity not just abstract symbols, but the actual shape of the cosmos, the actual geometry of space-time, the actual structure of the world we inhabit. Penrose has said that his motivation for developing CCC was not a desire to prove that the universe cycles, or a wish for immortality, or a need to find meaning in the endless expansion of space. His motivation was a puzzle, a specific technical puzzle about the nature of entropy and the initial conditions of the Big Bang. Why was the early universe so smooth? Why was entropy so low? Why was the Weyl curvature so small? These are questions that standard cosmology answers with inflation, but that Penrose found unsatisfying. He wanted a deeper answer. An answer that did not require a special mechanism within the universe, but that emerged naturally from the geometry of space-time itself. CCC is his answer. And whether or not it is the right answer, it is an answer of extraordinary beauty and depth. It takes one of the most basic facts about the universe, the fact that it started smooth and is getting lumpy, and turns it into a cosmic principle, a principle that connects the beginning of time to its end, the smallest scales to the largest, the simplest particles to the most complex structures. A principle that, if true, means the universe is not a story with a beginning, a middle, and an end, but a poem that rhymes with itself, over and over, in variations so subtle that only the most careful reader would notice the repetition. You are that reader. or you could be. By lying here in the dark, following this thread of thought from the Bekenstein bound to the cosmic microwave background, from Nietzsche's demon to Penrose's aeons, you are doing something that the universe, for all its vastness and patience, cannot do for itself. You are paying attention. You are noticing the rhyme. You are hearing the repetition. And in hearing it, you are giving it meaning. The universe does not need your meaning, but you need it. And that need, that hunger for understanding, that drive to make sense of the cosmos and your place in it, is itself a part of the pattern. It is one of the things that recurs, one of the features that the universe keeps producing, aeon after aeon, because it is written into the finite state space of the cosmos, and given enough time, everything that is written will be read. You are reading it now, as you have always read it, as you may always read it. Let us spend a few more moments with the evidence, not the contested evidence of Hawking points or the debated significance of CMB anomalies, but the quieter, more personal evidence, the evidence of your own experience. Have you ever had the feeling that a moment was more than it seemed? That a particular evening, a particular silence, a particular quality of light carried a weight that could not be explained by its circumstances alone? You might call it déjà vu, or nostalgia, or simply the sense that something important was happening, even if you could not say what. This feeling is not evidence of eternal return. It is not proof that you have been here before, but it is interesting that the feeling exists at all. That consciousness, this remarkable, improbable product of matter arranged just so, comes equipped with the capacity to sense depth in time, to feel that the present moment is connected to something larger, older, deeper than itself. Neuroscience has explanations for déjà vu. It is likely a glitch in the memory formation process, a brief failure of the brain's ability to distinguish between experiencing and remembering. The moment feels familiar not because it has happened before, but because the brain, for a fraction of a second, processes it as a memory rather than a perception. The explanation is mundane, and it is probably correct, but the feeling itself is interesting, because it shows that the human brain, this 3-pound organ, made of carbon and water and electrical impulses, has a relationship with time that is more complex than simple chronology. We do not merely experience time, we feel it. We sense its texture, we intuit its depth, and sometimes, in quiet moments, we catch a glimpse of something that feels like eternity. Whether that glimpse is real, whether it is a faint echo of a previous aeon reaching across the boundary into this one, or whether it is simply the brain's way of amusing itself, we do not know. But it is worth noting that the physics of eternal return does not require the absence of such feelings. It is entirely consistent with them. If your consciousness recurs, if the exact neural pattern that produces the feeling of "this has happened before" reassembles in a future aeon, then the feeling is accurate. It has happened before. You just cannot prove it. There is a deep irony in this. The one cosmological model that would make déjà vu literally true is the one model that prevents you from ever confirming it. The memories of previous aeons are not carried across the boundary. The conformal rescaling erases all specific information. You cannot remember a previous life, even if you have lived one, because the mechanism that would carry the memory has been dissolved along with everything else. The universe gives you back your life but withholds your autobiography. Let us also consider the relationship between CCC and another great mystery of modern physics, dark energy. The universe is expanding, and the expansion is accelerating. This acceleration was discovered in 1998, when two independent teams of astronomers found that distant supernovae were dimmer than expected, indicating that they were farther away than a universe expanding at a constant rate would allow. The universe was not just expanding, it was speeding up. The cause of this acceleration is unknown. Physicists have given it a name, dark energy, but the name does not explain anything. It is a placeholder for ignorance. The simplest explanation is that empty space itself has a small but positive energy density, a cosmological constant in Einstein's equations. This constant pushes the universe apart with a force that is negligible on small scales but dominant on cosmological ones. It is the reason the expansion is accelerating. And it is the reason the far future of the universe will be an empty, expanding void, rather than a collapsing crunch. Dark energy plays a crucial role in CCC. Without it, the universe might eventually stop expanding and contract, leading to a big crunch rather than a heat death. A big crunch would create conditions entirely different from those at a Big Bang, and the conformal rescaling that Penrose proposes would not work. CCC requires that the universe expand forever, that it approach a state of maximum entropy in an infinite future, and that this infinite future be conformally equivalent to a Big Bang. All of this depends on the existence of a positive cosmological constant, which is to say, it depends on dark energy. The fact that dark energy exists, and that it has precisely the properties needed for CCC to work, is either a remarkable coincidence or a clue. Penrose has suggested that it is a clue. He has speculated that the conformal geometry of CCC might provide a natural explanation for the value of the cosmological constant, which is otherwise one of the most puzzling numbers in all of physics. The observed value is extraordinarily small, roughly 120 orders of magnitude, smaller than theoretical calculations would predict. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved problems in physics. If CCC could explain it, that would be a powerful argument in the theory's favor. But so far, CCC has not provided a convincing explanation for the value of the cosmological constant. It has only shown that the existence of a positive cosmological constant is consistent with, and indeed necessary for, the conformal cycling that the theory proposes. This is suggestive, but it is not a solution. The cosmological constant problem remains open, and its resolution, if it comes, may come from a direction that nobody has yet anticipated. Let us also pause to consider the emotional landscape of these ideas. Because we have been talking about physics and mathematics and philosophy, and it is easy to lose sight of the fact that these ideas touch something deeply human. The fear of death, the longing for permanence, the desire to know that our lives matter, that they are not merely random fluctuations in an indifferent cosmos. The physics of eternal return does not provide easy comfort. It does not promise heaven or paradise or reunion with lost loved ones. It does not guarantee that your suffering has a purpose or that your achievements will be remembered. What it offers, instead, is something more austere and more strange. The possibility that your life, exactly as it is woven into the structure of reality so deeply that it cannot be removed. That the pattern of atoms and energy that constitutes your existence is as much a part of the cosmos as the gravitational constant or the speed of light, not a parameter in an equation, but a configuration in a state space, a point in an unimaginably vast landscape of possibilities that is, nonetheless, finite. And in a finite landscape with infinite time, every point is visited, every configuration is realized, Every life is lived. This is not the immortality that most people dream of. It is not a continuation of consciousness after death. It is not an afterlife. It is a re-life, an exact repetition that is, from the inside, indistinguishable from the original. You will not know that you are living again. You will not carry forward any wisdom or any scars, but you will live, the same life, the same joys, the same sorrows, the same moments of boredom and brilliance and confusion and clarity. Some people find this idea terrifying. The thought of reliving every painful moment, every failure, every loss, with no possibility of change, no possibility of doing it differently, can feel like a kind of prison, an eternal sentence without the possibility of parole. Others find it liberating, because if this life is the only life you will ever live, and if you will live it an infinite number of times, then this life is infinitely important. Every moment matters, not because it leads somewhere, not because it contributes to some larger narrative, but because it is permanent. It is the thing itself. The infinite repetition does not diminish the moment. It magnifies it. It takes the smallest, most forgettable instant and makes it eternal. And still others find in it a kind of peace, a release from the anxiety of finitude. You do not need to rush. You do not need to squeeze every drop of experience from every moment. You do not need to achieve greatness or leave a legacy or make your mark on the world, because you will be back. The mark will be made again. The legacy will be lived again. The experience will be had again. There is no urgency, because there is no end. Only the endless, patient, beautiful repetition of a cosmos that has nothing but time. Whichever response you feel, it is the right one. There is no wrong way to feel about infinity. There is no correct emotional response to the possibility that your life is eternal. The feelings are yours, and they are as much a part of the pattern as the atoms in your bones and the photons in your eyes. Let us also think about what this means for the people you love, because if eternal return is true, then it is not only your life that recurs, it is theirs as well. Every person you have ever known, every relationship you have ever had, every conversation, every touch, every shared silence, all of it, part of the pattern, all of it, recurring in the infinite cycling of the aeons. The people who have died are not gone, not in the deepest sense. Their patterns exist in the state space of the universe, and given enough time, those patterns will reassemble. The friend you lost, the grandparent who passed, the strangers whose lives briefly intersected with yours and then moved on. All of them, part of the deck. All of them, waiting to be dealt again. This is not a replacement for grief. It is not a balm for loss. The pain of losing someone is real and present, and cannot be erased by abstract cosmological speculation. But it is, perhaps, a different way of thinking about what loss means. If the pattern recurs, then loss is not destruction. It is interruption, a pause in an endless melody. The note will sound again. The theme will return, not because anyone wills it, but because the mathematics demands it. And perhaps that is enough. Perhaps the knowledge that the pattern endures, even if the awareness does not, is a kind of comfort. A cold comfort, maybe. An abstract comfort, but a real one, because it means that the love you felt was not wasted on something temporary. It was invested in something that the universe itself will repeat. Your love is as permanent as the laws of physics. Your connection to the people in your life is as enduring as the Bekenstein bound, as lasting as the cycling of the aeons. The night deepens. The stars wheel overhead, each one a nuclear furnace burning in the silence of space. each one a temporary structure in a universe that makes and unmakes and remakes without end. And you are here, beneath them, part of the same process, subject to the same laws, riding the same expansion outward into the dark. Let us take one more breath with the science before we let go, because there is a detail we have not mentioned, and it ties together many of the threads we have woven tonight. It concerns the nature of gravitational waves and their role in the transition between aeons. When black holes collide, they produce gravitational waves. These are ripples in the fabric of space-time itself, predicted by Einstein in 1916 and first directly detected by the LIGO Observatory in 2015. Gravitational waves travel at the speed of light. They are, like photons, massless, and this means that they survive the transition between aeons. They are part of the information that is carried across the boundary, part of the message that one universe sends to the next. In his March 2025 paper, Penrose proposed that there is an entire epoch in the transition between aeons that is dominated by gravitational waves. He called it the gravitational wave epoch. During this phase, the gravitational radiation from all the black hole mergers and evaporations of the previous aeon fills the universe, creating a kind of gravitational background noise that smooths out the transition and makes it more physically plausible. This gravitational wave background would carry information about the large-scale structure of the previous aeon, information that could, in principle, be detected in our own. This is a remarkable prediction. If confirmed, it would mean that the gravitational wave detectors we are building, instruments like LIGO and LISA and the planned Einstein telescope, might one day detect not just the gravitational waves from events in our own aeon, but echoes of events from before the Big Bang, the collision of supermassive black holes in a previous universe, reverberating through the boundary between aeons, arriving in our cosmos as a faint but detectable signal in the fabric of space-time. We are not there yet. The technology is not sensitive enough. The theoretical predictions are not precise enough. But the possibility is real, and it gives CCC a future, not just as a philosophical speculation, but as an empirically testable theory. A theory that makes predictions about what we should find when our instruments become powerful enough to look. And that is perhaps the most important thing about CCC. It is not a retreat from science into mysticism. It is not a surrender to the unknowable. It is a scientific theory with all that implies: mathematical precision, empirical predictions, vulnerability to disproof. It may be wrong, it may be right, but it is honest. It puts its claims where they can be tested, and it invites the universe to answer. The universe has not yet answered, but it will. In time. Because the universe, as we have seen tonight, has nothing but time. There is one more thing we should talk about before the night carries you away. Something about the relationship between physics and philosophy. Because the question of eternal return is not purely scientific. It is not something that can be settled entirely by observation and experiment. It is a question that lives at the boundary between what we can measure and what we can only imagine. And that boundary is one of the most fertile places in all of human thought. Physics tells us what is possible. It tells us that the Bekenstein bound limits the number of states. It tells us that Poincare recurrence guarantees return in finite systems. It tells us that CCC provides a mechanism for cosmic cycling. It tells us that quantum mechanics introduces randomness that may or may not prevent exact repetition. These are facts, as solid as facts can be in a science that is still evolving. But physics does not tell us what it all means. It does not tell us whether the recurrence of your physical configuration constitutes the recurrence of you. It does not tell us whether a life that is repeated infinitely is more meaningful or less meaningful than a life that happens once. It does not tell us whether the proper response to eternal return is joy or despair or indifference. These are questions for philosophy, for ethics, for the quiet, personal, unmeasurable realm of human experience. And they are questions that each person must answer for themselves, in the light of their own values, their own temperament, their own understanding of what it means to be alive. Nietzsche answered with amor fati. Love your fate. Embrace the repetition. Will it, as if you were choosing it freely, as if each moment were a gift you were giving to yourself across the aeons. This is a heroic answer, a defiant answer, an answer that transforms a potentially terrifying idea into a source of strength and affirmation. The Stoics answered with equanimity. Accept the cycle. Recognize that you are a part of a vast, impersonal, endlessly recurring process, and find peace in that recognition. Do not struggle against the current. Do not rage against the repetition. Simply live as well as you can, knowing that your life is one thread in an infinite tapestry. The Buddhists answered with detachment. The cycle is suffering. The goal is not to embrace it or accept it, but to escape it. To reach a state of understanding so profound that you are no longer bound by the wheel of recurrence. To achieve nirvana, the extinguishing of the flame, the liberation from the endless turning. And some people, faced with the idea of eternal return, answer with a simple, quiet gratitude, not for the repetition, not for the infinity, but for this. For the fact that they are here right now, in this particular configuration, experiencing this particular moment. For the sunset that will never be exactly this sunset again, even if a sunset very much like it will occur in a distant aeon. For the voice of a friend, for the warmth of a blanket, for the simple animal pleasure of being alive in a body on a planet under a sky full of stars. There is no right answer. There may not even be a meaningful answer. The universe does not come with instructions. It does not tell you how to feel about its structure. It simply presents itself in all its beauty and strangeness and leaves the interpretation to you. And perhaps that is the final gift of the physics of eternal return. Not an answer, but a question that, once asked, cannot be unasked. A question that changes the way you see this moment, this breath, this evening, this life. A question that makes the ordinary extraordinary and the temporary eternal. The question is simple. It is the question Nietzsche's demon asks. If you were told that this life exactly as it is would repeat forever, would you embrace it or would you despair? The answer you give in the quiet of your own heart says more about you than any theory of cosmology ever could. Let the thought settle. Let the numbers fade. Let the names of the physicists and the titles of the theorems and the details of the evidence dissolve into the background, like the cosmic microwave background itself, a faint glow that is everywhere and nowhere, carrying a message that is older than the stars. The message is simple. The universe is vast. Time may be infinite. And you, improbable, temporary, beautiful you, are a part of it. Not a visitor, not an accident. A part, a recurring part. A part that the universe keeps making, because it can, because the math allows it, because the deck has only so many cards, and given enough shuffles, your hand will come up again. The stars are patient. They burn for billions of years without complaint, converting hydrogen to helium, helium to carbon, carbon to oxygen, building the elements that will one day become planets and oceans and the bones of living things. They do not rush. They do not worry about running out of time. They simply burn steadily, faithfully, for as long as the fuel lasts. And when the fuel runs out, they do not vanish. They transform. They become white dwarfs or neutron stars or black holes. They become something else. Something that endures in a different form, for a different span of time, serving a different purpose in the great economy of the cosmos. You are like that. You burn, not with nuclear fusion, but with the slower, gentler fire of metabolism. The chemical reactions in your cells, the electrical impulses in your nerves, the steady rhythm of your heart, these are your fusion, your way of converting matter into energy, energy into motion, motion into thought. And when your fuel runs out, as it will, you too will transform. The atoms that made you will not disappear. They will scatter. They will be taken up by other processes, other systems, other forms. They will become soil and air and water and eventually new stars. And if CCC is right, they will become you again. Not in some vague poetic sense, in the most literal physical sense possible. The same atoms, or atoms exactly like them, arranged in exactly the same way, producing exactly the same thoughts, in exactly the same order, in an aeon so far from this one that the distance between them cannot be expressed, in any number that has a name. This is the weight of the idea. This is what Nietzsche felt when the demon whispered in his ear. This is what the Stoics meant when they spoke of palingenesis. This is what the Hindu sages meant when they described the breathing of Brahma. Not a metaphor, not a wish. A possibility, grounded in the deepest physics we have. A possibility that, even if it can never be proven, can never quite be dismissed. Rest now. You have earned it. You have traveled further tonight than most people travel in a lifetime. Not in miles, not in light years, but in understanding. In the depth and breadth and sheer vertigo of the ideas you have held in your mind. The stars are still burning. The photons are still streaming. The cosmic microwave background is still whispering its ancient message to anyone patient enough to listen. And you are still here, breathing, thinking, wondering, alive. That is enough. It has always been enough. The universe does not ask more of you than this. To be here, to be aware, to wonder, and to rest when the wondering grows heavy, and let the night carry you where it will. The cycle continues. The aeons roll on. The photons fly. And somewhere, in the mathematics of it all, in the equations and the theorems and the subtle patterns in the oldest light, there is a place for you, a configuration, a pattern. A U-shaped space in the fabric of reality that has been filled before and will be filled again. Sleep well. Dream of stars. Dream of light. Dream of a universe that does not end, that only transforms, that sheds its skin and emerges, shining new and impossibly familiar. Think, as you drift, of the photons, those ancient travelers, born in the nuclear furnaces of stars, or in the faint glow of Hawking radiation, or in the hot plasma of the Big Bang itself. They are the one thing that connects every part of this story. The photons that left the surface of the last star in the previous aeon. The photons that carried the Hawking radiation of the last black hole. The photons that filled the dying universe with a faint, uniform glow. The photons that crossed the boundary, conformally rescaled, and became the blazing radiation of a new Big Bang. The photons that cooled and stretched as the new universe expanded, becoming the cosmic microwave background. The photons that, 13.8 billion years later, pass through this room, through your body, through the spaces between your atoms, carrying a message from the dawn of time. They are the thread, They are the continuity. They are the one thing that endures across the boundary between aeons because they have no mass. And without mass, there is no time. And without time, there is no ending. The photons do not die. They do not decay. They do not grow old. They simply travel at the speed of light, forever, carrying the shape of the universe with them, from one beginning to the next. If you could ride a photon, you would experience the entire history of the universe in a single instant. Birth and death, creation and destruction, the formation of galaxies and the evaporation of black holes, all of it happening at once in a timeless, scaleless, eternal now. You would not experience the transition between aeons because there would be nothing to experience. No gap, no pause, no boundary, just the continuous, unbroken, infinite journey of light through a cosmos that keeps reinventing itself. You cannot ride a photon, but you can imagine it. And in imagining it, you are doing something that the photon cannot do. You are understanding it. You are seeing the journey from the outside with the eyes of a conscious being and recognizing its beauty. The photon does not know that it is eternal, but you do. And that knowledge, that awareness, that capacity for wonder is the rarest and most precious thing in the universe. The night is deep, the cosmos is wide, and you are held gently by the same gravity that holds the planets in their orbits and the galaxies in their clusters. The same force that will, in the far future, gather the last photons into the faintest possible glow. The same force that, if Penrose is right, will carry that glow across the boundary into a new beginning. You are part of that force, part of that glow, part of that beginning. Good night. And if the physics is right, and the aeons keep turning, and the patterns keep forming in the infinite patience of time, then this is not goodbye. It is only good night, because we will do this again. You and I, the words and the silence, the questions and the wondering, the stars and the dark, exactly like this, exactly this way, forever.